Good morning, good afternoon, good evening. This is the ABC of stars and galaxies. So this is the second talk in the series of the universe half an hour at a time. Last week I was talking about the beginning of everything, describing how the universe made all of the hydrogen in 3 minutes, and now we're going to see what happened to all of that hydrogen. How did it get used? So we're looking at various structures out there in the universe, all of these wonderful galaxies that we see, some of them spiral, some of them other shapes. But how did all of these galaxies and all the stars within them come to be? So we're going to be looking at the A, B and C. A is for accretion. Galaxies were formed by the matter created in the Big Bang accreting, or accumulating if you prefer, under the influence of gravity. That's a fairly long-term process. It takes billions of years. We'll see that in due course. Black holes, we believe, are at the centre of most, if not all, galaxies. These are very large black holes, so-called supermassive black holes. Some of them are very active. We see some galaxies in which the black hole is eating up, feeding on the matter around it. Matter is falling into the black hole, creating huge amounts of energy. There is a black hole at the centre of our Milky Way galaxy, but that appears to be quiet. In other words, matter is not falling into that black hole, and so we don't see a huge amount of energy coming out. The third point that determines how galaxies behave is C for collisions. Collisions and mergers of galaxies over billions of years determine how galaxies grow and how they ultimately evolve. So there's the ABC we're going to talk about. The ABC of stars, well, we haven't really got time in half an hour to cover all of the detail of what's going on at the heart of a star. We can't cover all the details of nuclear reactions, for instance, but we can give you a very brief idea of how stars work. So how do you make a star? Well, you can follow 3 relatively easy steps. If you start with a large enough cloud of hydrogen, and we've already said that the hydrogen was made in the first 3 minutes after the Big Bang. If we start with a cloud of hydrogen, then follow these steps. Step 1, wait. Step 2, wait some more. Step 3, wait a bit longer, and you're done. Okay, you now have a star. In other words, if you start with enough hydrogen and you let gravity do its stuff, as long as you've got some patience and are prepared to wait 1 million years or so, you will end up with that hydrogen cloud collapsing under gravity and making a star. But we need to understand something about the mechanisms and how that works, and is it really that simple, or is there more to it than that? We can only really understand what's going on if we look at computer simulations. We can't stare at a star and watch it evolve. We can't stare at a galaxy and watch it evolve. So we have to rely on computer simulations in which we put what we think is all the necessary physics into a computer program, and then we simulate how galaxies came to be and how they evolve and how stars are born and how stars live and die. There are lots of simulations. Don't worry about the picture on the left. That's just a snapshot of lots of simulations that exist and have been carried out in the last decade or 2. I'm just going to pick one of those sets of simulations. It happens to have the name Illustris, so I'm going to take images and videos from the Illustris simulations in order to illustrate points in this particular talk. We don't have to worry about the fact that there are dozens of other simulations. So one of the simulations starts right from the beginning of the universe, when we start with a load of hydrogen where the density is not quite the same everywhere. We can let gravity do its stuff, and what we find is the universe collapses into this so-called cosmic web structure of filaments and voids. Voids where there doesn't seem to be much matter, and filaments, and where filaments cross we have these knots of high density. You can see these white blobs there. This is where the galaxies are forming. We'll have a look at that in more detail in just a second, but first a word about the simulations themselves. In principle, the simulations can run from right after the Big Bang to the present day, or into the future, if we so wish. The idea is, if we run these simulations, if we think we've got the physics right, then we should end up with a universe which looks, in the computer simulation, a bit like the actual universe we see out there. And so that would indicate that we've got the physics right. But along the way, a lot of different factors have to be taken into consideration. It's not simply a question of start with a lot of hydrogen and wait for gravity to work. That's the idea of the right-hand panel. But also we have to worry about the left-hand panel, for instance, the fact that the universe is full of this stuff called dark matter, which we don't really understand. I was talking last week about the creation of all the hydrogen and helium that we see to make the stars and the galaxies. But in fact, there's more dark matter than there is all of the hydrogen and helium that is in the observable universe. So we don't understand what this dark matter is. It doesn't seem to make stars, but it has mass and therefore it affects gravity. So we do have to take it into account in these simulations. And the middle panel reminds us that as we are starting to form galaxies, we are making stars, and during a star's lifetime it emits a lot of light and other radiation, and perhaps when the star dies it might emit a huge amount of radiation. And this outflow of radiation when stars live and die, that can actually impede the infall of matter that gravity is trying to do. So we have to take all of this into account. And hence these computer simulations can be rather complicated, somewhat more than I've indicated in this brief explanation. So that's why these computer simulations require huge amounts of computing power, large supercomputers and programs that run for weeks or months or even years to carry out these simulations. Hence the sort of simulations that I'm showing here today, they can only really be carried out in the last decade or two when we had sufficient computing power. So let's return to that picture we saw a moment ago of the cosmic web, and let's home in on just one small part of that. Let's look at an area where a couple of filaments meet, where we have a white blob indicating that we've got a rather high density of matter starting to form here. Let's see how that ends up looking like a galaxy. This, as you can see from the top right, is called the illustrious TNG. Illustrious is just the name of the simulation. It happens to be version 2 of the computer program, and instead of calling it version 2, they've called it the next generation. Hence, illustrious TNG. If you want to know more about these simulations, just have a look at the link at the bottom of the slide here. You'll have the link in the handout after the talk. So let's have a look at what's going on inside that red circle as matter is starting to collapse under gravity and starting to form a galaxy. So now we're looking in detail, and we can run this simulation for a few billion years and see what happens. We can see matter is falling in from above, and it's coming in from the left, and it's coming in from the right, and it's producing a chaotic mess in the middle where the matter is starting to get more and more dense. In this simulation, lighter colours correspond to higher densities and darker colours correspond to lower densities. We can see more and more of the matter falling into this central region, swirling around, very chaotic to start with, but after a little bit of time we can start to see structures forming. And we can start to see how this structure is starting to eat up any smaller structures around it. At this particular point, although it's still rather chaotic, we can start to see the hint of spiral arms starting to show in this galaxy. And the scale on the left-hand side tells us that this structure we're looking at is about the same size as the Milky Way galaxy. If we look at galaxies that are out there, this particular spiral galaxy is a beautiful one that happens to be face on, so we can see the spiral structure in incredible detail. But what I'd like to point out in this is the fact that you can see a lot of these little pink regions. Hydrogen glows red, and so these areas of pink are hydrogen-rich regions. These are hydrogen nebula, or hydrogen clouds if you like, that are in the process of collapsing, and this is where stars are being born. These pink areas are effectively stellar nurseries. And we can see these within our own Milky Way galaxy. For instance, you might be familiar with the Great Nebula in Orion. And here is a very detailed image, again, of a hydrogen cloud which is in the process of collapsing, and right in the heart of this, stars are being born. We can get an idea, again, from a slightly different simulation, this one carried out at the University of Exeter. On a much smaller scale, we can get an idea of how stars are born, rather than thinking about simulations on the galactic scale. So here we have a cloud of hydrogen. It's spherical just because that's easier for the computer to deal with. Most clouds, of course, are rather more ragged, but in this simulation we're starting with a spherical cloud of hydrogen, and it has a little bit of variation in density, which we can't really see as we look at it at the moment. There are small variations in density, and individual parts of this cloud have been given a small random nudge in a random direction to start the process off, to make it a little more realistic, so that as gravity takes hold and we run forward 1 million years or so, we can see how this hydrogen cloud collapses. Again, the lighter colours correspond to denser regions of the cloud. And as the denser regions get denser and denser and hotter, what can happen is that hydrogen can actually start to fuse together. If it's hot enough, if it's dense enough, hydrogen can fuse together to make the next element, helium, and in the process release energy. This is the process of nuclear fusion. And that's how we find these stars are being made. Each little white dot is a new star being born. So you can see that this cloud of hydrogen wasn't simply big enough to make half a dozen stars. This cloud was actually large enough, perhaps many tens of light years across. It was actually large enough to make perhaps thousands of stars. And you can see some of the stars are being made and stay close to where they're born, but you also notice that some of these stars are flying off at great speed, and these stars are leaving the cluster that's being left behind. If we zoom out and have a little bit of a twirl, we get an idea of the 3D structure of this star cluster that's been made. Notice that the hydrogen cloud, which started off spherical in this simulation, is now rather ragged, and not all of the hydrogen has been used up. Some has been used to make these stars, but there's still hydrogen left for future star generation. So if we ask the question, this sort of simulation produces what we see as this collection of white dots, does that look anything like the star clusters that we see in the Milky Way galaxy, for instance? Well, if we compare that simulation with an actual photograph of a star cluster, I think you'll agree that yes, it seems to give us most of the right sort of elements of what we expect in a star cluster. Our Sun does not appear to be part of a star cluster at the moment. It appears to be just an isolated star. But it was probably born in a cluster like this. Remember some of those white dots that seem to go flying out of the star cluster? Well, that's probably what happened to our Sun. It was probably born along with a whole load of other stars, but for some reason our Sun left that cluster 4.5 billion years ago when it was born. It's almost impossible to backtrack and find out where our Sun actually came from, so we can't identify which particular star cluster was the one that possibly gave birth to our Sun. Okay, so we know where these star clusters and individual stars come from, but we can ask ourselves what's going on in terms of the mechanics inside a star, the dynamics that dictate how a star behaves. And although in principle we could talk about the ABC, we're only going to talk about the B. The most important factor when we're thinking about stars is balance. Gravity is pulling in, trying to compress the cloud of hydrogen, either before or after the star has actually ignited and started to produce nuclear reactions. Gravity is always pulling in, and if the density is high enough, as I mentioned before, it's possible for hydrogen to fuse together into helium and release energy. And that radiation comes from the core, where the cloud is hottest, and that radiation can provide an outward pressure. So gravity is pulling in, radiation is pushing out, and it's the balance of those two forces that is critical in the way stars behave. If those two forces are balanced, then the star is stable, the star is happy. But if for any reason those two forces get out of balance, if gravity is no longer in balance with the radiation, the star must change. The star must evolve. And we can actually describe essentially all aspects of star birth, star life and star death in terms of these opposing forces and these balance of forces. Let's have a look at how stars are classified. This will be convenient for what we're about to see in terms of the star's life cycle. It's convenient to plot all the stars that we can see on a scale of luminosity on the vertical scale. This is how bright the star is, not how bright it appears to be in our sky, but how bright it actually is relative to the luminosity of our sun. And so our sun, which is near the middle there, by definition has a luminosity of 1. And the horizontal scale is the surface temperature of the star, which for our sun, the surface temperature is a little less than 6,000 Kelvin. Stars with a slightly lower surface temperature would be further to the right, and stars with a higher surface temperature will be further to the left. We'll have a look at some of the other stars in this diagram when we've thought about the life cycle of stars. Excuse me. So if we start with the hydrogen cloud that we saw earlier, we know that that can produce a large number of stars. Let's just think about one of those stars. Let's imagine a hydrogen cloud is collapsed and part of that cloud has got hot enough to start nuclear reactions. So hydrogen is fusing into helium and releasing energy. If that star was, for instance, the same mass as our sun, then the process of nuclear fusion will continue for many billions of years. Our sun is about 5 billion years old, and the nuclear fusion will continue probably for another 5 billion years or so. But eventually that fuel is going to start to run out. And if we remind ourselves about the idea of balance, if gravity is trying to compress the star and the nuclear fusion is producing radiation that's pushing outwards, when the fuel starts to run out, what's going to happen is the star is going to compress because gravity wins over the nuclear radiation. As the star compresses, it gets hotter, and what that can do is start to inflate the outer layers of the star. And so the star, if you like, puffs up to become a so-called red giant. And because our star isn't particularly massive, it doesn't actually have enough gravity to hold on to that outer layer of the star, and that can simply be lost into the space between stars. It can be lost into interstellar space and produce what is called a planetary nebula. The name is a bit of an anachronism. They are nothing to do with planets. The name simply comes from the fact that they were confused with planets in the very early days of astronomy. So a planetary nebula is a large cloud of hydrogen that results when a star blows its outer layers off into the interstellar medium. What's left after that is blown away is just the very hot core of the star, where the nuclear reactions used to be taking place but have now stopped because the fuel has now run out. So what we're left with is the white dwarf, as it's called. It's the core of the star, which is relatively small. It's only about the size of the Earth or so, about 10,000 kilometers or so in diameter. Very small compared to the original size of the sun, but very hot. So it's small, hence dwarf, and it's very hot, hence it's white hot. If we go back to that diagram, we can see where red giants and white dwarfs fit into this classification scheme. Remember, there was the sun near the middle, and red giants are up here. They are very large, so they're very luminous, so they're higher up than the sun, but they're relatively cool, with a surface temperature of only 3,000 Kelvin or so, so they occur in this diagram to the right of the sun. The core that's left when the star has lost its outer atmosphere, the white dwarf, remember that's very small, so it's not particularly luminous, so it's a little bit further down in this diagram, but it is very hot, hence it's further to the left than the sun. And that's one of the reasons that we classify stars by putting them in this diagram of luminosity and surface temperature, because by seeing where a star occurs in this diagram, we can get some idea of what it's doing. Is it stable and quite happily burning hydrogen to helium? Or is it a red giant coming to the end of its life? Or is it a white dwarf which has already lost its outer layers? If we come back to the idea of the evolution of a star and the lifetime of a star, if we return to the left and think about that cloud of hydrogen, we can ask, well, what happens if instead of making a small star, what if it happened to collapse and make a relatively large star? And by large, I mean a mass, let's say, 10 times as massive as our Sun. Well, if you think again about the balance, the force of gravity is pulling in and radiation is trying to balance that. If we have a very massive star, we have very strong gravity, which means the star has to burn its fuel, has to fuse hydrogen into helium very quickly in order to provide enough outward pressure to balance gravity, because the mass is so large. So this large, massive star will get through its fuel very quickly. If it's massive enough and the core of the star becomes hot enough, it's not only possible to take hydrogen and fuse them together until we make helium, it's also possible to fuse helium together into heavier elements like carbon and nitrogen and oxygen, the sort of atoms that we are made of, and can also make heavier elements like silicon and iron. But sooner or later, even a massive star will come to the end of its life. And when that happens, it can be absolutely catastrophic if the mass of the star is very large. The collapse of the star when the nuclear fuel runs out can happen. The core of the Sun, the core of the star, can collapse in a matter of seconds, and the explosion that results can actually rip the star completely to pieces. It's what we call a supernova. What's left, the core, just before the star actually explodes, there's a huge compression of the core of the star. And that core can end up as a very small object, such as a neutron star, which is only a few kilometers in size. Remember, a white dwarf was about the size of the Earth, but a neutron star would only be a few kilometers in size. And if the original star was massive enough, then the compression of the core can compress so much matter into such a small volume that the gravity is so strong, not even light can escape. And that object in the bottom right-hand corner there is what we call a black hole. So regardless of whether a star ends its life as a white dwarf or a neutron star or a black hole, one thing that we can note from this diagram is that quite a substantial amount of the star is actually blown away and recycled back into interstellar space. And remember, a star might have been fusing hydrogen into helium, and possibly helium into carbon and nitrogen and oxygen and silicon and other elements. And these elements also get spread and back into the interstellar medium. So the original hydrogen cloud starts getting seeded with some heavier elements. And if another star is born from that cloud, then the star will start from mainly hydrogen, but also with a lot of these heavier elements in place. And this cycle can continue round and round again as the material that's thrown out of a star, either gently at the end of its life if it's a small star, or catastrophically if it's the end of the life of a massive star, all of this material can get cycled round and round and round. On Earth, we know that the Earth's crust is made of lots of heavier elements. It's made of aluminium, and it's made of copper and nickel and iron, and there's also silver and gold in there as well. So there's lots of heavy elements in the Earth's crust. So that means the Sun cannot have been born simply from a cloud of hydrogen. It must have been born from a cloud of hydrogen which already had heavy elements seeded into it from previous generations of stars. In other words, stars lived, died, generated heavy elements, cycled round, another star was born, generated some more heavier elements. They were recycled back into the interstellar medium, and round it goes until the sun came along as maybe a fourth or fifth or sixth generation star, and that's how we end up with all the elements we see on Earth. If you remember your periodic table of the elements, even if it was only on the wall of a schoolroom perhaps, let's just dim that down slightly and remind ourselves there's hydrogen in the top left, there's helium in the top right. Carbon is a relatively lightweight element, but of course it's very important for life on Earth. And we can explain all of the elements up to iron in terms of the life of a star. We can think about heavier elements being made by hydrogen fusing into helium, helium fusing into carbon, carbon fusing into heavier and heavier elements up to iron. But if we want to explain the existence of even heavier elements, such as for instance silver or gold, which occur beyond iron in the periodic table, they can't be explained in terms of the processes that occur during a star's life, but a star death can produce these elements. When a massive star goes supernova, so much energy is released, iron and all the other elements can be fused into, well, essentially any element in the periodic table. And that explains why, when we look around on Earth, we find a periodic table of 92 different elements, even though the universe only started with essentially hydrogen and helium. Stars are not just ways of making light and heat, they are ways of making all the elements that we know about. So we can look at stars in our immediate neighbourhood and we can start to understand how they work. But we can ask the question, what's going on right at the heart of our galaxy? Remember, we are quite a long way from the centre, and we can see in our night sky the thousands of stars that we can see with the naked eye are all relatively close to us. But what's going on in the centre of the galaxy? Well, with a large enough telescope we can peer towards the centre of the galaxy and we can look at stars that are orbiting very near what we think is the very centre of the Milky Way. And there we find stars orbiting around something that's invisible, but must be very massive in order to keep these stars orbiting the way they do. If we measure these stars, we find that that object, we believe, must be a black hole. It is so massive and apparently so small, a black hole is the only thing that seems to fit the bill. If we make measurements of lots of stars, we can't do this quickly. We have to watch these stars for perhaps years to see how they are moving and how they are looping around in their elliptical orbits. If we measure that over a period of time, we can calculate how massive must the object be in order to keep those stars moving the way they do. And we find that object doesn't have something like the mass of the Sun. It's not 10 times the mass of the Sun or 100 times the mass of the Sun. The object that is keeping those stars in their orbits is something of order 4 million solar masses. And the symbol on the right there, capital M, circle dot, is simply a shorthand symbol for the mass of our Sun. There's nothing special about the mass of our Sun, it's just a convenient unit to use because using kilograms or tons gets a bit ridiculous. So there's an object there keeping these stars in orbit that has a mass of 4 million solar masses. But it must be tiny in order to have these orbits. If it was large, these stars would collide with it, so it must be very compact. It can be no larger than our solar system. So we have a very massive object which we can't see occupying a very small volume. We determine that this object must be a black hole, a region of space from which light cannot escape. And because it's substantially more massive than a single star or 10 stars or 100 stars, it's obtained the name of supermassive black hole. So there's such an object at the centre of our galaxy, and as far as we can tell, there's a similar object at the centre of perhaps not every galaxy, but certainly a very large fraction of the galaxies we've looked at all appear to have a massive black hole at the core. We haven't been able to obtain an image of the black hole at the centre of the Milky Way, but by combining lots of radio telescopes together a couple of years ago, it was possible to obtain a picture of this, which is what's going on in the centre of the galaxy called M87. This was chosen because it's a large galaxy with what appears to be a black hole not of a mass of millions of solar masses, but a mass of more than 6 billion solar masses. And what we're looking at there, the orange donut if you like, this is a false colour image showing us radio emission, and this orange donut is telling us that matter is falling into the black hole, and as it is doing so, it is getting very hot and emitting lots of energy. And that's what we're picking up from a distance of some 50 million light years or so. We can't see the black hole itself, it's somewhere right in the middle there. No light is coming from the black hole and therefore we can't see anything. But we can see the glow of matter that is falling into the black hole. If we take a snapshot of a galaxy, we can't see the black hole here because it's far too small and it's simply completely washed out by the fact that we've got so many stars in that region. So in the optical part of the spectrum, we can't see anything unusual going on. But we can, of course, obtain lots of snapshots like this of galaxies. And all of the galaxies look rather serene and somewhat static. We know they're rotating, but it might take 100 million years or so for a galaxy to rotate. And we haven't got the time to sit and watch them. We haven't got the time to sit and watch them evolve. If we want to understand the evolution of galaxies, well, we can get a hint by looking at those galaxies which are not in total isolation. Some galaxies seem to be interacting with their neighbours. This one, for instance, seems to be distorted. The two components of this galaxy, or these galaxies, appear to be interacting with each other and distorting each other. But we can't really get the full picture from lots of static images like this. And again, this is where simulations come into play. We can run simulations over billions of years and watch galaxies interact with each other. And this simulation from Illustris is showing that again. So now we're talking about distances which are much larger than individual galaxies, and we can see here hundreds of galaxies in this soup, and we can see how all of these galaxies are interacting with each other. We can see two large galaxies getting very close towards the centre here. They've just passed close to each other, and they are going to pass close to each other once more, and then they are going to merge together. So this, we think, is very common. Based on these simulations that have been carried out, we now find that this sort of interaction of lots of galaxies and galaxies merging with each other, and sometimes large galaxies gobbling up smaller galaxies. You can argue that galaxies are cannibals, they eat each other in the early days of the universe, and the large galaxies that we see today have probably merged with lots of other galaxies in their history. Let's just run this again because it's quite a nice little simulation. It doesn't seem to want to. Okay, let me just go back to it and run it again. So again, every time I watch this video, I see something new in terms of what the galaxies are doing. If you look at a particular galaxy, it might happen to get close to one of its neighbours and get very distorted. But again, if you watch the two galaxies getting close to each other towards the centre, there goes another galaxy which is getting very distorted. The two in the centre are passing through each other and then eventually merging together. And these simulations have been run under various conditions, and the question is, when we look at this image here, is this the sort of thing we see? If we run this simulation and that tells us we would expect to see a lot of small galaxies and a certain number of larger galaxies, is that the sort of distribution that we actually see in the universe when we take, for instance, Hubble images of close and more distant parts of the universe? So by running these simulations and comparing them with observations, we can see if we've got a reasonable understanding of how galaxies form and how galaxies grow during their evolution over many billions of years. So just in summary, to remind you that when we're talking about stars, what really matters is the B. of the ABC. It's all about balance. Gravity trying to shrink a star, and the nuclear reactions at its core trying to expand the star, and it's all about the balance of those two forces that dictate how a star originally switches on, how it lives its life, and how it might die. For galaxies, the ABC is all about accretion. In the early universe, the hydrogen started to accrete to form these galaxies. Black holes are at the core of most, if not all, galaxies. Some are active in the sense that matter is falling into the black hole, others are less active. We don't really understand what's going on, in the sense that we don't really know whether black holes started to form first and then the galaxies form around them, or vice versa. Did galaxies form and then the black holes at the centre start to grow? I'll be saying more about black holes in next week's talk. And the final element of the ABC is C for collisions. Collisions and mergers have been responsible for the changes to galaxies, the evolution of galaxies, right from the early universe to the present day, and will continue to be part of their evolution for billions of years to come. Thank you for listening to the ABC of stars and galaxies in half an hour.